In this section, we'll show you how to create comparisons. In the comparison section of the website, you can see a list of the comparisons you've previously conducted, or if you haven't made any comparisons, you can explore publicly available comparisons. To create your own comparison, click the Run Comparison button, and you'll be presented with a user interface where you can select the test and benchmark sets for the comparison. Typically, the test set is a file that you've uploaded that you want to benchmark against a well-established benchmark set. There's a few benchmark sets that the precisionFDA website suggests because these are commonly used by participants, and to avoid too many clicks, you can actually just select one of those. In this case, I'm going to select the NA12878, also known as HG001, truth dataset published by NIST, version 2.19. This was used in the first precisionFDA challenge. And as a test set, I can choose any VCF. When I click on Select File, I'll be presented with all the VCF files that are publicly available on precisionFDA, as well as my private VCF files. And I can actually do a search or a filter here for choosing the file name. So I can choose my VCF file. I can optionally provide a bed file, which will constrain where the comparison will be conducted within the genome. But note that when I chose the NIST dataset, it automatically chose the bed file provided by NIST. So that's all I need to provide in this particular example. When I click the Compare button, I can name my comparison, or by default, it will suggest as the name of each one of the two sets. So when I click Start Comparison, this will launch the comparison, which will be pending for a few minutes until the cloud behind the scenes conducts the comparison. When the comparison is done, let me switch to an example of what this looks like when it's done. I'll see a page which will show me statistics such as number of true positives. These are the number of variants that are common in both sets. False positives, which are the number of variants that are present in the test set but are not in the benchmark set. So they were identified as positives, but that was a false thing. And then false negatives, which are entries that are in the benchmark set but did not get identified in the test set. So negatives that are missing from the test set. And based on these three numbers, the system also calculates entities like precision, recall, and their harmonic mean, which is the F measure. In the bottom, you'll also notice this curve, which shows how precision and sensitivity change as we threshold the genotype quality score. So in most VCF files that come out of VCF tools such as variant callers, there is a genotype quality score annotation. And if we threshold this and choose increasingly higher thresholds for higher quality, then we will remove some of the variants. And if we redo this precision versus recall experiment again, we'll notice that as we increase the threshold, the precision typically gets higher and the sensitivity gets lower. So we start from this down here, which is a score of 0, where there is no threshold. And as we increase the threshold, we'll notice that the sensitivity gets lower and the precision gets higher. And the steeper the curve, some people believe the better the underlying algorithm. When we're looking at the comparison, we can also download the outputs by clicking the Output tab here and looking at these files containing the list of false negatives, false positives, and true positives, as well as the data points that were used to create that curve. We can also give feedback to NIST if we believe we've identified a problem with any of the NIST truth data, or we can click Visualize to take a look at some of these variants in the context of a genome browser. Thank you.